Hi, this is Mr. Mitchell. Let's have a video about magnets. Here are your 5 questions about magnets. Magnets. Magnets are involved in many different devices, more than you might expect. Anything with an electric motor, refrigerators, some locks, sometimes cabinet doors have magnets, and many other devices. Now, some rocks, like this one right here, are actually magnetic. You may have studied in earth science about a mineral called magnetite. Magnetite is this rock. Now, when people first realized this, they didn't call it magnetite. The first ones that were found near Greece were called lodestones. Lodestones you may hear in other courses. Well, anyway, magnetite is a permanent magnet. It's always magnetic. You can see here it's magnetic to the materials that are attracted by magnets. Now you can actually change a piece of iron or other materials into a permanent magnet by stroking it several times with a permanent magnet. So we know these lodestones here are permanent magnets. So if you find a smooth side to it, you can scrape a piece of iron with it and it will make the iron a permanent magnet. Now, a permanent magnet doesn't always stay permanent, especially the ones that become a permanent magnet. They can be weakened or even removed by doing things like adding heat to it, or even hammering it a lot. Isn't that odd? But even when doing that, some materials do tend to hold on to their magnetism better. We have called what's magnetically hard magnets and what's magnetically soft magnets. And since I don't have my board here, I'll just put H for hard and S for soft. Magnetically hard materials are hard to get to magnetize, like cobalt and nickel. If you were to rub cobalt or nickel up against the lodestone here, then it's hard to get it to magnetize, but it's hard to demagnetize it once it is magnetized. That would be magnetically hard. Oh, and what a bad arrow there. I'll go ahead and write out hard and soft since we have it here. So something like cobalt or nickel are hard magnets. Hard to magnetize, yet hard to demagnetize. Now we've already mentioned an example of a soft magnet. Iron is a soft magnet, which means it's not that hard to get it to magnetize, but it can be demagnetized fairly simply. Now magnets have a north and south pole. Now here's a magnet, a bar magnet, and one side is north, magnetically north, and one side is magnetically south. Now, you know, we just got through studying about positive and negative ions, and that's exactly what's going on here. You have all the positive and negative ions in opposite ends of the north and the south pole. So what will happen is, if you have, oh, I'm trying to remember which it happens to be right here, but if you have a positive end and a negative end, they are attracted to each other. That's why the north and south ends of the poles will attract to each other. And that's also why the south end and the south end, for example, and the north end and north end repel each other, because you don't have like ions attracted to each other. The two north poles repel, a north and a south pole attract, the two south poles repel. So like signs repel, opposite signs attract. It is impossible to isolate the poles. If you cut the magnet, you still end up with a positive end and a negative end. Here's an example here. You have one magnet here, say it was cut. You still don't isolate one end as positive, one end as negative, or north and south. And no matter how many times you cut it, even into little bitty tiny pieces, you will still have a north end and a south end of each magnet. It's kind of interesting, I think. Magnetic fields. When magnets repel or attract to each other, it's due to the interaction of their fields. As you notice, if you take a nail here and get it close to this lodestone, the nail, if you let it go, will cling to it. So it's not just if it touches it that you have the attraction. And you may remember whenever we talked about electric fields, we had something along the lines of this, where we had a positive and a negative side, and it has kind of arrow or lines going out of the positive and negative side. The positives and negatives attract. You can draw the same type of field with a magnet here. You have the north end, you have the south end, and you have these magnetic fields which go out. So if you have, say, the north end is one sign here, and you put some kind of other object out here which is a positive or the opposite type sign, then it is in the magnetic field. It would be attracted to it and come toward it. So that's a little bit about the magnetic fields. They are identical to the electrical field lines you studied with electricity. The attracted charges form closed loops. The attractive charges form closed loops, and you can see that especially through here. All these lines out form closed loop because we have one side that is attracted to the other side, and no matter what charge you have an object of, it can be charged to one or the other side. Now that's if it has a charge. Now not every object is attracted to magnets because every object doesn't carry a charge. The closer the lines, the more the attraction. The closer the lines, the more the attraction than it is, say, on a larger line. So you can kind of draw this. If something is more magnetic than something else, they would have close lines around it. Say you have something which is like iron, and it's kind of losing its magnetism, then you don't have close lines around it. You have wider lines around it, which means, let's say this was iron. If you have something like a nail here, you might drop the nail and the force of gravity may be stronger than the attraction it would have here. But if you have something that's a stronger magnet here, say you've magnetized some cobalt, or it just happens to be a stronger magnet, if you have a nail here, the force of gravity might not be strong enough to keep it from being attracted to the magnet. The lines, of course, get farther away the farther away it is from the poles. So the farther out, the farther the lines will be from each other. Now, we do have an object we're all familiar with that has to do with magnets that one want to talk about, and that is the compass. A compass, you can see an example right here, is a magnet suspended over some kind of pivot so the arms can swing freely. So what that does, this compass aligns with the Earth's magnetic field. Yes, the Earth acts as a big, giant bar magnet. So whenever you have a compass here, it will align itself. This north end will be attracted to the North Pole. Now you may notice that we don't have north right up here, and I'll explain that in just a second. It's up for debate amongst the scientific community why Earth acts as a magnet in the first place. Well, it may be because of the Earth's iron inner core. You may remember back in Earth science, they studied that the inner core of the Earth is made of iron and nickel. That may have something to do with it because those are items that can be magnetized, but it's still kind of something that we're not quite sure about. But for whatever reason, the Earth acts as a magnet. The Earth's magnetic field has actually shifted over time, and currently The North Pole has, yes, you guessed it, the south end of the magnet at it. And currently, the north end of the magnet is at the South Pole. And like I said, throughout the course of geologic time, that has shifted. There have been times when scientists think the north has been facing north and the south has been facing south. And it's something that is kind of unique in that fashion. The magnetic poles are not at the same place as the axis, and you can see that right here. I'll change colors. Here the axis would be right at the top of the globe. The globe is spinning around this axis, yet magnetic North Pole is just a little ways away. So whenever your compass is pointing toward the North Pole, it is pointing toward this magnetic North Pole, not exactly at the same place as where the axis runs. And like I said, ironically, the North Pole is where you find the south pole of the magnet, of Earth's magnet, and the South Pole has the north end of the Earth's magnet. So what happens is, to avoid confusion, we often say that this is the north-seeking pole, or the south-seeking pole. That's how we end up making that distinction. Well, make sure you go back and do the questions. Hope you've learned a little bit about magnets. And hey, don't forget to read about this in your science book.